Okay, so let's extend what we know about vectors in 2 dimensions to vectors in 3 space. So in 2 dimensions, we had an x-axis and a y-axis, and that divided the coordinate system into 4 sections, which we called quadrants, 1, 2, 3, and 4. Now in 3 space, we're going to have an x-axis, a y-axis, and a z-axis, which is going to divide our space into 8 regions, and we call those regions octants. And those are 3-dimensional regions. So I've got a picture here which will try to demonstrate to you or show you to help visualize what the octants are. So when we're graphing, the general perspective that's usually taken is the positive x-axis is coming out from the screen a little bit to your left. The positive y-axis is going to your right. And the positive z-axis is moving upward. So if I consider the xy plane, which I have in this picture as blue, a blue parallelogram, that represents the xy plane. There's 4 sections above that, and there's 4 sections below that. The sections above it, let's start with where x is positive, y is positive, and z is positive. That's referred to as the first octant. Where x is negative, y is positive, and z is positive. That's the second octant. For the third one, it's where x is negative, y is negative, and z is positive. Octant number 3. And finally, when x is positive, y is negative, and z is positive, that's the fourth octant. And then underneath that xy plane, where z is negative, we have the remaining octants in the same order. So 5 is underneath octant 1, and then 6 to the back right, 7 in the back left, and then 8 in the front underneath 4. So there's your octants. Now, when we have a point and we want to plot that, we need to give it 3 numbers. So instead of an ordered pair, we'll use an ordered triple to represent a point. So for example, 5, 2, negative 3, we would move positive 5 in the x direction, 2 in the y direction, and then negative 3 in the z direction. So there is some graphing software nowadays which makes it a lot easier to visualize this than trying to draw it in 2 dimensions. So the next thing I want to investigate is how would we find the distance between 2 points in 3 dimensions? So let's say I have a point P and Q, and P's coordinates are x sub 1, y sub 1, z sub 1, and Q has coordinates x sub 2, y sub 2, z sub 2. What I'd like to do is make PQ the inner diagonal of a cube. So if I create a cube around that, and then I want to label one other important vertex of this cube, and that's in the back right lower corner, and I'm going to call that R. So I need to give coordinates for R. Now I don't want to say x sub 3, y sub 3, z sub 3, because R is related to P and Q. So if you notice, what is the x coordinate for R going to be? Well, for R, it's going out exactly the same amount as Q is, because Q is right above R. So Q and R will have the same x coordinate. So I can call that x sub 2 as well. Likewise, the y coordinate for R, how far to the right does R go? The same as Q did to the right. So R and Q also have the same y coordinate, so I'll label that y sub 2. What about the z coordinate? Well, obviously Q is a lot higher up than R is, so it has a different z coordinate. But R and P are both on the bottom of the cube, the plane that covers the bottom of this cube, so they have the same z value. So the z coordinate for R will be the same as the z coordinate for P. So that's z sub 1. All right. Now, if I connect P to R on the bottom of this cube, that's going to help create a right triangle, which I've drawn in green. Right triangle PQR, where PQ is the hypotenuse, QR is a leg, and PR is a leg. And for a right triangle, we know the sum of the squares of the leg equals the square of the hypotenuse. So I know that PQ squared is going to equal PR squared plus QR squared. So let's figure out, so the distance from P to Q will just be the square root of PR squared plus QR squared. So we need to figure out what is PR. Well, since PR is on the bottom of the cube, which represents a plane, that's really two-dimensional, so I can ignore their z-coordinates, which are the same, and I can use the distance formula to find PR. So PR is going to be the square root of the difference of the x's squared plus the difference of the y's squared. And then what about the distance from Q to R? So Q to R, notice that Q is directly on top of R, so I can simply subtract the z-coordinates, and that'll give me the distance from Q to R. So Q to R is going to be z sub 2 minus z sub 1. Now if I move back over to my calculation for PQ, it's going to be the square root of PR squared. Well, PR is the square root of this, and so when I square PR, that cancels the square root, and I'm left with just x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So, see if I can write small. X sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And then Q sub R here is just z sub 2 minus z sub 1. So Q sub R squared will be this quantity squared. So z sub 2 minus z sub 1 squared. And so it should be no surprise that that looks exactly like the distance formula in two dimensions, except we've just added one more quantity, and that's the difference of the z values. So let's make sure we understand that. Find the distance between these 2 points. So I go ahead and hit pause, calculate it, and then check your answer. So to find the distance, it's going to equal the square root of the difference of the x's. The order doesn't matter as long as you're consistent with which point you're using first. Negative 2 minus 3, the difference of the y's squared, and the difference of the z's squared. So that's going to give me the square root of 9 plus negative 5 squared is 25 plus another 25. So the square root of 59, which is 7 point something, close to 8. And that's it. That's all there is to it. All right, so let's move on and talk about some of the things that we've done with vectors in 2-space and extend that idea to 3-space. So let's have 2 points, A and B, with those coordinates. Write the component form of the vector AB. Well, how did we do this in 2 dimensions? We did terminal minus initial. So it's the same exact idea in 3 dimensions. The component form of AB, it's going to be the vector, and terminal minus initial. So we're going to take the x components and subtract them. 2 minus 3 is negative 1. And then subtract the y's. So 1 minus 0 is 1. And subtract the z-coordinates. 4 minus a negative 1 is 5. And so there's your component form of vector AB. Negative 1, 1, 5. So to get from A to B, we go negative 1 in the x direction, positive 1 in the y direction, and then positive 5 in the z direction. How about writing AB in terms of the unit vectors I, j, and now we have the vector k. So what are these in 3D? Well, I used to be 1, 0, so now it's 1, 0, 0. J was 0, 1, so now it's 0, 1, 0. And k is going to be 0, 0, 1. So to write our vector AB in terms of these unit vectors, we have negative 1i plus 1j plus 5k. And you don't need to write the ones, obviously. But there's the unit vectors. So we've written AB in component form and in terms of the unit vectors. Two different ways of representing the same vector, AB. Find the magnitude of AB. Well, how did we do that in 2 dimensions? So you're going to find that everything we want to do in 3 dimensions, just go back and think, how did you do it in 2 dimensions, and extend that idea. So to find the magnitude of AB, we did the square root of the x component squared plus the y component squared. So follow that pattern, the y component squared. And then, of course, yes, we're going to add to that the square of the z component. So that gives us the square root. 1 plus 1 is 2. So we get 27 total. And then we can simplify that a little bit. And so that'll be 3 root 3. So that's the length of that vector. By the way, if I wanted a unit vector in the same direction as AB, because we've done that before, then I would just take the magnitude and multiply it by my vector, negative 1, 1, 5. I'm sorry, divide it. So I'm going to take the normal vector and divide it by its length. And so I'm going to get negative 1 over 3 root 3, 1 over 3 root 3, comma 5 over 3 root 3. And that'll give me a vector that's in the same direction as AB, but will have a length of 1. And then obviously you would rationalize each of those components. All right, so what if I have another vector v? So I'm going to call AB, the vector AB I'll represent as W. And then I have the vector v, which is 2, negative 3, 1. And so maybe let's write AB underneath here. That was the vector negative 1, 1, 5. Find the dot product. Well, we remember the dot product. It gave us a number for an answer. We need to do 2 vectors. And we multiplied the x components, we multiplied the y components, and we added those together. So same idea here. We're going to multiply the x components, negative 1 times 2. Add to that the product of the y components, 1 times negative 3. And then we're going to extend this and add the product of the z components, 5 times negative 1. So negative 2 plus negative 3 is negative 5, plus negative 5 is negative 10. And so the dot product is negative 10. And if you remember, when did we use that, or how did the dot product help us? It helped us find the angle between 2 vectors. So the angle between 2 vectors we get by using the equation cosine of theta, if theta represents that angle, is equal to the dot product, so W dot B, over the magnitude of each multiplied together. So we've already figured out the dot product. And I'll take the inverse cosine of the right side. So the dot product was negative 10. And then the magnitude of W represents AB, we figured out its magnitude up here, so that was 3 root 3. Or I'm just going to leave it as the square root of 27 for now. And then we need to find the magnitude of V, So the vector v was 2, 3, negative 1. So I'll do that over on the side. The square root of 2 squared is 4. Negative 3 squared is 9. Negative 1 squared is 1. So that's the square root of 14. And we're going to need a calculator to figure out this angle. It's not one of those special right triangle angles. So we'll grab the calculator. And we'll do, let's make sure we're in degree mode. And we'll do the inverse cosine of negative 10 divided by, I'll combine these two square roots, so 27 times 14. And we get 120.9536, etc. So if we round this, I guess we could say it's 121.0. And that's degrees. So if you think about two vectors and the angle between them, it makes sense that we're going to get an obtuse angle because the dot product wound up being a negative number. And the cosine is negative between 90 and 180. Okay.